presentation is about visible spectroscopy and investigating how concentration affects the absorption of solutions. This presentation is going to include visible spectroscopy, the spectrometer, which is how we measure absorption, how light affects solutions, such as colours, and do an experiment with food colouring to explore this with methods, results, and discussions, as well as how concentration affects absorption of different solutions with methods, results, discussions, and references at the end. Visible spectroscopy is a technique that measures the amount of wavelength of visible light that is transmitted by a sample in reference to a blank one, such as water. This is an example of a spectrometer that we would use in an experiment to measure absorption. You would put the solution in the cuvette in the corner of the box, and it would run through a light would run through the solution, and you would get your absorption on a screen. As we decided to do a digital computer, as it looks clearer and you can get better results. The spectrometer has got a light inside which reflects a beam onto a grating, which refracts all the separate colours and wavelengths within the light, and it would pass through a slit, which would then hit the solution, and any wavelengths that are not absorbed by the solution would go through the solution and hit the detector, and it would show a wavelength digitally on a computer screen. Light is a form of energy that allows us to see. It is a part of the electromagnetic spectrum, and the electromagnetic spectrum ranges from shorter wavelengths like radio waves and larger wavelengths like gamma waves. And right in the middle of this is visible light, which ranges from 780 nanometers to 380 nanometers. Shorter wavelengths of light carry more energy, and longer wavelengths of light carry less. The Beer-Lambert law is a principle in spectroscopy that relates to the absorption of light in properties of the substance where the light is passing. It is expressed in the equation shown here. And A is for absorption, and the epsilon is the molar absorptivity, B is the path length of the light through the solution, and C is the concentration of absorbing species. Another way of seeing this is absorption is directly proportional to the molar absorptivity, and absorption is directly proportional to path length through the light, and absorption is directly proportional to concentration. So, for example, if concentration was to increase, then the absorption would increase. For the first experiment, you would have 7 jars filled with purple, pink, orange, yellow, green, blue, and black solution. A cuvette would be 3/4 filled with one of these inks and placed in the spectrometer and ran through the computer to collect some results. The results would then be put in a table like this one, and it would record the very peaks of each solution on the computer. As you can see from our results, it shows that the blue absorption peak is 629.4 nanometers, which makes sense as it usually falls around 630, as the complementary colour to blue is red and orange, which means that the red and orange would be absorbed and the blue light would be reflected. And it was also our first time using such equipment in experiments, so next time we do the experiment, I think we should familiarise ourselves with using the spectrometer and the digital readings so we can get an even more accurate result and run our solutions with even more accuracy. When doing the lime cordial experiment, instead of having the solutions ready-made, this time we would have to make up the different concentrations of solution before running them through the spectrometer. So for this experiment, we first doubled the solutions of cordial that were measured, as the volumetric flasks that were used were 10 millilitres, while it called for a 5 milliliter volumetric flask. So we used a pipette filler bulb for even more accuracy and filled up the volumetric flasks with the different amounts of cordial, and then filled up the rest of the volumetric flasks with water right up to the blue line. And then we mixed it thoroughly so that we had an even concentration throughout the volumetric flask and ran that through. However, during this part of the experiment, we realised that the cordial solutions that we were measuring were just not absorbing, didn't have enough high absorption, like they should be higher. And the unknown solution was coming out higher than the concentrated, which we know wouldn't be possible, as the Beer-Lambert law says that the most concentrated solution would have the most absorbance. So we realised that we would have to do the experiment again, as we didn't have the correct solution to get the results we needed. So Instead, we swapped the solutions as the unknown cordial was 0.6 stronger, 0.932, and the concentrated cordial was 0.3. So the unknown cordial was much stronger than the concentrated, meaning that the labels must have been mislabeled because the concentrated is the highest that we could get in absorption. So we tried it again, and we swapped the solutions around, and as you can see from the old results, they are very low down. They're below 0.5 for the absorption. And the newest results, you can see the absorption is above the 0.5 mark, and the unknown is around here. So the least diluted concentration and the most diluted concentration, the unknown falls between them, so we know we're on the right lines, and we were able to use these results to find the unknown. We put our results in this table, and we can see from our results that as the concentration goes up, the absorption also goes up, which is in line with Beer-Lambert's law that absorption is directly proportional to its concentration. We put our results in a graph, and using the trend line, we were able to calculate the unknown with the existing results. Using the graph, we estimated the concentration unknown was around 25%. This makes sense, as the unknown absorption falls somewhere between 20 and 40. And considering that the unknown was very close in absorption to the 20%, as the 20% was around 0.288, and the unknown was around 0.305. So they were very close in concentration. In conclusion, from the experiment we carried out, we can confidently say that the absorption from each solution follows Beer-Lambert law. That absorption is directly proportional to concentration, and by using our results to find any unknown solution concentration further proves that spectroscopy is an accurate and useful way to identify substances and determine their composition. The mistakes made during this experiment helped us further understand what was happening, but trying again made our final results even more accurate and allowed us to come to a final result that we could use to calculate our unknown. However, next time I think that we should get a better understanding of the equipment before we start the experiment, as using a spectrometer for the first time can cause confusion and more mistakes. During my presentation, I used a couple of references. The first reference I used was to get the diagram for the light slide, which was the electromagnetic spectrum. So I used some information from there. And the next link I used was, and the one after, was to define how a spectrometer worked. And the last link at the bottom was I used to make my own diagram so I could better understand how a spectrometer worked. And there was also a YouTube video by here that goes through it in detail, and it helps you better understand how a spectrometer actually works, which helped me